Yeah, hi, I'm having fun. I hope you too. I've brought some utensils with me. So let's get started. I have 70 slides and this is the first one. So what is scheduling? You probably all know the problem. You want to cook, you want to do some sports because your doctor told you. You need some sleep and you need to work. And you can't do this at the same time, so you can't sleep and do sports or sleep or work. Albeit whatever. So what you do, you need scheduling because you essentially one CPU and you need to kind of schedule. And what we normally do, we have certain time slots where we do them. For example, most people sleep between like 10, 11 in the evening and like 8 o'clock in the morning, whatever. But that's essentially how we do it. We cook at certain times, we eat at certain times. But processors also need to do this because we typically have the problem that we have a few tasks. For example, currently on my laptop there's a couple of IDEs running, a Firefox and a document viewer, and they all want to come onto the CPU and do some work. And then we have CPUs 1, 2 in this example, but let's reduce it down to an example that's more manageable. And here we have just one CPU and 2 tasks. So what happens is that we could, of course, just let a process 1 run. That would be totally fine. The system would be really well utilized. But problem is task 2 would be starting and it would be pretty much useless, especially if task 2, as you see later, is our mouse driver and our desktop that tries to show the mouse. But we typically want to have is that, for example, task 1 runs, then task 1 is either kicked from the CPU or it says like, hey, I'll wait for something. Task 2 comes along, task 1 gets along. And then task 2 doesn't want to run, so task 1 gets another chance, task 2 comes on, and so on. And that's pretty cool. And we need to automate this somehow. The important thing is here, when they talk about tasks, I essentially mean what you all know as like threads and processes mixed. So process is essentially a task group leader, but don't be confused by the terminologies. I think about tasks like the processes that we want to schedule, just because processes usually have multiple threads. So what are our typical scheduler goals? One goal is fairness. So we want to ensure that all tasks come onto the CPU in the manner that is given by the priorities. So that's pretty important. Then we want to utilize the resource. So we want to use more than one core in my 16-core machine here. We want to reduce the overhead. So if we're scheduling a lot of things and we're scheduling all the time, like for example every nanosecond or so, and scheduling takes like 100 nanoseconds, then it's pretty useless because our system is just stuck in doing scheduling decisions. So we need to be smart there too. And of course, what's especially important with modern machines like laptops, because we work with them, is their responsiveness. And here what you have to think about is that you have a clash between essentially 2 main classes of programs. We have on the one hand I/O bound. These processes are waiting, these tasks are waiting usually for I/O. For example, it's your web server, it's your game that like every 1/60th of a second gets events from your mouse and wants to emit something on the screen. And then there's CPU bound processes, for example, like many compilers that do optimizations, or like math computation stuff. I don't know, probably also Bitcoin mining, I don't know. But the problem is here, typically in our systems, there are only a few implemented on our system. Most people here, if you use Linux, you only use one, but it depends on the Linux version that you're running on. So probably the Debian users out there, they might be running a different scheduler than the Ubuntu people, because I think in Linux kernel 6.6, the scheduler changed. But anyway, essentially you only use one at a time, which is not that great, because the Linux scheduler CFS is the one that came till 6.6. But this also holds true with newer ones. CFS was built in a simpler time. So we had a time where CPUs looked like this. Pretty simple. You had a free cache, you had a few cores. Transitioning between cores was pretty expensive because we had cache effects and such. So it was pretty nice. We could have simple assumptions. Our core topology was also quite simple, but that's not how it looks nowadays. And these slides, by the way, are by David Werner, the kernel developer, who knows what he's talking about. The architectures nowadays are much more complicated. You have heterogeneity in the cores. For example, in my smartphone, I have 3 different kinds of cores in the CPU alone, and that makes scaling far more complex. Then you have non-uniform memory access across different cores, across different LLCs, and so on. So especially with lots of different applications, probably one scheduler shouldn't rule it all. As you all know, in Linux we have like 15 or more different desktop environments, because we all are like, yeah, we want to have choice, but in this case we currently only have one, so that's not that great. So let's create our own. Has someone of you wrote a scheduler before? None? No, let's check. Why? Have you a Linux scheduler, I mean?
For us, schedulers to, how to arrange things.
Okay, yeah. Some of you might have wrote something on the service, yeah, but okay, none of you did, so hopefully after this talk you start your own. Let's see. How hard can it be? Of course, it's probably pretty simple. Yeah. Don't ask me how much vacation I had last year in summer when I tried to implement parts. Anyway, it's not that hard, especially because we have now eBPF, which I tell you in a minute about, and Sched. Sched is the project here with the logo. And I have stickers if you want one later. So the idea is with eBPF, if you don't know about it, eBPF is a crazy technology. It's like putting JavaScript in the Linux kernel. It's important he didn't mean that as an insult. Brandon Craig, when he told this to, I have to always stress this, he meant it as a cool thing, because it's essentially how you can how when JavaScript was invented, it was put into browsers so that web application can be more interactive, that you can do more stuff as a user and without modifying the browser, and that's the same here. That's how it looks like when he shouts at hard drives to show latency measures. That's how it looks normally when it doesn't show at hard drives. On the count of shouting, prepare yourself, we're going to shout at my laptop later. Because I've invented a new version of frequency scaling. Anyway, how does eBPF work? It's pretty simple. You write your program, typically in C code, and it's a small program that hooks then later into things like the network interface. Then you compile down to something like a pretty simple bytecode. Essentially, it represents a really simple machine model so that you can easily later put it on many machines. Then we load it into the Linux kernel via system call, then we go through verify. The idea is that we check that it doesn't have any, for example, infinite loops and such, so we have some guardrails, and then we put it into a JIT compiler because we want to run it fast, and we can attach it. We can use this to implement, for example, load balancer. That was one of the major things that people did. For example, at Facebook, their load balancer runs for years now on eBPF, and you can do this with other tools too for security things and such. But then people started to think about, hey, couldn't we do this with schedulers too? Couldn't we just say, okay, we have now the ability to extend our Linux kernel at runtime. Let's do this. Let's do this for schedulers too. So to quote Tijin Hui, who is one of like the people in the Linux kernel maintaining this kernel, and who also proposed the first Linux patch for it, he wrote, one of the goals was the ease of experimentation and exploration. So it is far easier when you don't have to recompile your Linux kernel all the time to experiment. And especially when you don't crash your system all the time, because even if you do something stupid, it's probably fine. The Sched will catch you, and that's pretty cool. You can use this to customize schedulers. You can take an existing scheduler, there are a few of them out there. You can modify it and have fun, as we see in a minute, and you can rapidly deploy it, because essentially you only have to call a system call to load it in, and that's all. You don't have to restart your system. And for all of you wondering, This came in with Linux 6.12. So with the next Ubuntu release, you'll have it. I think the Fedora users already have it, and Arch probably has it since December when it came out. In the following, I'll be using an example applications because the idea is that I show you a few schedulers, and this is Slow Roads. It's a pretty nice Creative Commons licensed video game where you essentially drive a car through the hillside, and it shows us easily the frames per second. And we can because it's an easy IO-bound application where we can directly see things. So the structure of the following is I'll give you the idea of the scheduler and tell you kind of how it works, then I show you the implementation in a bit, I show you C code as you all expect here, and then I give you a demo where we run it, and then we modify values and have fun, and maybe crash our system. Live demos are always a risk, so I would also call it having fun with schedulers, because that's what we're surely having. Doing video games on Sundays is always nice. If you want to try it yourself, it's pretty simple. Just download it from here. It's a minimal scheduler repository. You need minimal dependencies. You should have a modern Clang compiler installed, and I think 1 or 2 dependencies, but it's mentioned there, and you can find more explanations there. Yeah. Now, the first scheduler that I'll be showing you is the first come, first served scheduler. It's pretty simple. The main idea is, hey, task, run as long as you want. We won't stop you. Just run as long. I'll trust you. You won't do anything bad. I trust you. You won't talk to CPU. Let's see how it goes. And so, let's see how it goes. And for all the schedulers, I put down the QR code that links you directly to the file so you can see the scheduler. And it's all GPL licensed, so for all of you are there. So here's the game, just running. Put it in auto drive so it moves. I can even put sound on if you like. We can try whether it works. It doesn't work. Fine. Oh, is this a, no. Oh, we should put this in here. Ah. Okay, whatever. Just assume we could also emit sound, but I think it's kind of annoying when I'm talking alongside. So let's go into the scheduler. We have here our first come first served scheduler. It's pretty simple. So at the start, what we do, we initialize a scheduling queue because that's really important. We need something where we put the tasks in. And we create a queue here, and then a little bit below, we have a method that is always called by a task when it's like, oh, I want to run on the CPU, please. And then it's called this way. So what we do here, the first come first served is pretty simple. We just tell like, hey, we push you into the queue. We give you a slice that's essentially infinity because that's -1 means in unsigned in is infinity, so it can run forever. And then whenever CPU is like, hey, scheduler, I want to run something, please, then it calls the Sched dispatch method, and it gets parsed to CPU where we're currently in, and then we essentially tell it, hey, please move a task from the global queue, from the shared global queue to your local queue, and that's all. We can run it, and if everything goes well, it should work. Always the hardest part, getting your password correct. Cool. I register a scheduler. The scripts are also included in the repository. Let's play the game. And you see, nothing really changed. The problem is always when nothing changed, I'm like, did the scheduler really? Is the scheduler really running? Yes, it is running. We can just check it by using the sudo file system here. So no change at all. Should we run something alongside? Probably yes, because the system is currently not under load. I hope you trust me. It's a fairly efficiently written game. So what I want to do, I just run a Java build, like OpenJK build alongside. Many other people do like kernel builds. In those situations, I'm doing Java builds. And you see, I'm just compiling. It's just essentially compiling a large C++ code base. Not great. And what's even funnier is that's fine because it's compiling. The task stopped. They have to wait for you. There's also stress ng, and essentially launches 16, and this is an 8-core machine with hyper-threading. So we have 16 hardware threads, and he launches them, and they like to hog the CPU. Any guess what happens when I start this with my system? Yes, it locks up. Let's see how it goes. I'll try to wiggle the CPU. I hope you see that I try to wiggle the mouse. You see that there's a lot of happening. I can do things. I can switch. I can really work. It's like the poster child of a working scheduler. If I'm honest, it's really efficient. The resource utilization is 100%. It has 0 overhead. So if we just go by the criteria, exact like responsiveness and fairness, it's a pretty decent scheduler. So let's see. Yeah, now it works again. And why does it work again? If we take a look, the scheduler was kicked. And that's the cool thing is we did something wrong, but as you see here, it's an excerpt of the kernel source code, and if you're doing SchedX, you're looking a lot at kernel source code. Essentially, you can give a timeout, and what this does, every time a process waits more than 30 seconds in a queue. Like essentially when a process from time enqueuing to dispatching, when it's longer than 30 seconds, it essentially terminates your scheduler. And that's pretty cool because you saw we did a terrible mistake. We run a scheduler that doesn't work. Our system is like for 30 seconds in responsive, and that's cool. And otherwise it works. So now let's go on to another scheduler. There's the first come, first out scheduler, the FIFO scheduler. Essentially, it's like the saying, the early bird eats the worm. It's the early bird eats the early task, eats the time slice. It essentially means that we pick the first, every time a CPU is like, I want to run something, it picks the first one. And we can see this in code 2. Let's go over it. We initialize the queue as before. And we insert it, and then what we do, we set here time slicer. That's all we do. It's a pretty simple scheduler, and it works really well. What you notice here, what we're also doing, it's a tiny optimization, but it really helps, is that we tell it, hey, please scale the time slice by the number of processes waiting in the queue. So it means when the system is overloaded, the time slice gets shorter. This just means that the system doesn't get irresponsive when it's like flooded with tasks. And let's do it. Start FIFO. Now we have the scheduler. So this is pretty pointless. It works as before because the system is not on load. Yes, give it some. Let's look this, and you see, it still works. I'm running SysNG that like pricked my system before, and it still works, and it's pretty cool. So you see, it's tiny modification improves it quite a lot. And that's like a scheduler that you can actually run. You can use the schedulers, and there are use cases where this scheduler is better than eBPF, the default scheduler, because it's predictable, which is cool, and because it's not as complex, so you can easily modify it. And it's the scheduler that when I do some experimentation, I usually just take a FIFO scheduler because it's good enough. It's like half the FPS, fine, but that's okay. Interesting. I've never pressed Control-C in this game. You say I'm a really big gamer. Anyway, let's see how it goes. We stop it. And now to the other scheduler. So then there's another scheduler that's called a lottery scheduler. It's pretty simple. Life is a lottery, so should scheduling be. And that was a scheduler that was proposed like in around 30 years ago. So pretty early. It was a good idea. They thought at the time, but there are reasons why it was never a properly like merged into the Linux kernel. So essentially the idea is only the lucky task. Are you the lucky task who gets the time slice? Maybe you are, and then you get on the CPU. The idea is essentially not too different from what you might expect. Is essentially we put all the tasks into like a bowl, and the more priority a task has, the more tickets it has in there. So we can easily implement multi-priority scheduling without any more advanced queues. And then essentially every time a CPU is like, I want to do something, it just picks it. The only problem is the implementation, and I'll show you now why. Because if we take a look at the lottery scheduler, the first part is pretty simple. You've seen this before. We're creating a queue, we're inserting it. That's fine. What's the problem is here? So. What we need to do, we need to find a scheduler, and even if we don't have any priorities, because we need to walk over the queue sequentially because of implementation details. So what we do here, we pick a random number, and that's cool. eBPF has lots of things that we need. For example, give me a random number, and we get it one. And then what we do, we essentially walk till the element's index is lower than the random number here. The problem is, we have to always walk them, and that's slightly inefficient. And it doesn't give that many advantages compared to other schedulers, but it was a cool idea at the time, and that's why I implemented it. And if I'm honest, this was one of the first schedulers that I had some experience with, because when I showed you in the beginning that I was like, oh, we need to schedule a burger and something, I was doing this during my university time. I was like, lottery scheduling sounds nice. Let's do it for learning. So I got cards with like the different exams that I had to learn for on it, and then randomly draw tasks. The problem was I liked some topics more than others, so I cheated, and so it didn't work out because I had implicit priorities that weren't reflected in the appropriate priorities, because I also had some kind of affinity for a different task. Anyway, let's run it. Let's run it. Now it's running. Yeah, as before, this runs fine. I hope we have an interesting behavior now. And that's one of the reasons why it's not good for games. As you see here, the FPS number is really, really variable. That wasn't the case with FIFO. So you see it jumps between like 31, and maybe it goes down now. It's pretty weird behavior, and you don't want to have this with games. So when you talk with people, I talked with someone from NVIDIA, and he was like, the gamers are all focusing on they're focusing on the 95% latency. Oh, you see, just by chance. And I think consider this, you're playing like Counter-Strike, and why? Yeah, because. Wasn't it lucky? It's like Russian roulette now. Isn't it fun? This could be the new. You have to like. It's like playing D&D with your computer. Anyway, you see, there are reasons why it didn't catch on, and we didn't have the problem with FIFO. And you see, like, it was a cool idea at the time. Yeah, do a lottery scheduling, but you see here. Nah. The problem is also you saw that like, yeah, we can easily implement priorities. That's nice. The only problem is we have to walk through all the queue twice because we have to collect the weight sum. So it's like, yay, but double the overhead. So usually that's not a skill that's currently implemented. Let's stop it here just because we need to progress. Then, of course, you might think, what are like the modern schedulers based on that? Apparently not based on lottery scheduler, especially if you played some games recently, but they're based on something different. So essentially, fairness is really important. And how we can do it, we can track virtual runtime. It's kind of the runtime when we ignore priorities. Essentially, it tracks the time that the task had on the CPU in a specific time frame. And so the idea is we always run the task with the shortest rerun time in a specific slice of time first. The idea is when a process has many short bursts, then we want to prioritize it because we assume that it will further only have short bursts. For example, the game typically has short bursts of things on the CPU. And the long tasks, they run really a long time, so it's fine if they aren't coming on like every 10 milliseconds. And that's really cool because we can use this to implement a fair scheduler. So it's basically like saying, you already run quite a long time, didn't you? Let's choose another task. And now here, for the math nerds in there, we can also formalize this, and that's taken by Andrea Rigi's talk at FOSDEM on the topic of gaming and SCHED. Essentially, we assign every task a weight. That means the priority, and then we have the runtime, and the runtime is proportional to its weight, and the rerun time. And so essentially what we have here, we want to make sure that the runtime for a task is proportional to its runtime proportion. Of course, as you see here, we scale it by weight, especially because we want to have different priorities. And yeah, we implemented this by rerun time, which is a scaled runtime version. Now we can try it. We'll see. That's the most complex scheduler you see here implemented. The init is the same. There's also select CPU, which essentially you don't have to typically implement it, but what you can do is like, oh, if I find a CPU that's currently idle, just push it on there. It's fine because we want to do resource utilization. But then what we do with NQ, and I wrote a blog post on this, so you can read more about this. But essentially what we do, we track the V time alongside and then insert it into the queue based on V time, and the queue is a priority queue. So we don't have to care about whether it's a red-black tree or something. Linux kernel developers know how to develop these data structures. And of course, we track when it's running, when it starts running, when the task is stopping, and take care. And also, it's also important when a task newly comes in, we give it like the current maximum rerun time. Because otherwise, when the task comes in and doesn't have, like after 2 hours of the system working and we don't give it the initial rerun time, it would have rerun time 0. And that would be cool for the task because it could hog the CPU for ages. That's not good. So let's start, and hopefully it works. Hopefully it works. Nice. I made a change this morning. You shouldn't do changes before testing. Okay. The problem is it's a really simple bytecode, so we need to. It can only do divisions on like unsigned integers. Because I think they probably didn't want to implement the semantics for this. Anyway, let's see. The game runs as before. And then let's do something like compiling. And the game runs. It's relatively nice, doesn't it? It's probably the best scheduler as we had before. Yes, it fluctuates a bit more than FIFO because it's less predictable, but it gets us like 10 FPS more than the other schedulers, which is pretty decent, I think, for a simple scheduler. That's still, you see it here, that's still like 30, 40 lines of code in all. And let's try it with the thing that should also working, like with StressNG. And you see here, of course, the system is now doing more on the CPU, but still, the game is in a kind of playable state, if I might say. Albeit our system fully occupied. And of course, we could modify this by setting priorities, by optimizing this, but that's a task for like scheduler developers. And now let's stop this here. what's important is that we can develop much more complex schedulers. For example, the VTEM scheduler is essentially the basic version of like the completely fair scheduler that is implemented in your modern systems, just with much more code to catch like all the corner cases. The idea is here with the modern scheduler with eBPF, the earliest eligible virtual deadline first schedulers, they like to have long abbreviations. Essentially, it's lag-based, so it's the lag is the difference between the ideal runtime and the actual runtime of a task in a certain slice. So essentially, a task is then eligible when its lag is larger than 0. So essentially, when it can still run in its time slice, when it hasn't exhausted its time frame. And so we use this to calculate the priority that's slightly different because it takes into account the virtual time, as you saw before, the virtual runtime, like with our VTEM scheduler. And it takes into account that we only schedule it when the lag is larger than 0. And that's a pretty cool scheduler. But in the end, the VTEM scheduler is a pretty good model for like modern schedulers. So now what else can we do? Of course, we can implement some good schedulers. Fine. As I showed you, CFS was built in a simpler time. That's why people got up, for example, at Meta and also at NVIDIA and started to develop good schedulers. For example, the people at Facebook, they layered their own schedulers based on SchedX on many of their workloads because essentially what they can do is they put more domain knowledge in the scheduler because they know what they're running on the servers. The Linux developers, they don't know what you're running on your laptop. And that's probably a good thing, but they don't have any knowledge. You could be using eBPF for a server workload. Yes, you could be using it for a gaming workload on your small handheld device. Cool. You could even be running it on your smartphone or your smartwatch or whatever. They don't care. But you can improve your performance if you do care. There are many schedulers here in the ESCX repository. Some named like VD40 because it's like the lubricant for it. It's implemented in Rust, which is funny because shouldn't it be implemented in C because VD40 removes Rust. Anyway, then there's also BPF-land, which is essentially a gaming-focused scheduler implemented in eBPF, and it got good results. To quote Phoronix, we're implementing a Linux Rust scheduler in eBPF shows very promising results. And Andrea Rigi in his FOSDEM talk showed us that you can play Counter-Strike while compiling your Linux kernel, and both work, and that's pretty cool. Anyway, that's the story here. Essentially for gaming performance, as I told you before, primary metric for performance is essentially the frames per second. And so we need to focus on this. And if you want to learn more, take a look at this talk. Now we still have a few minutes left. So let's do some experiments, because I think you all saw at this nice conference a lot of people talking about really, really interesting stuff that could be applicable in the real world. But if I'm honest, we're also here for the fun. So let's check. That's something that someone I did a talk at FOSDEM sent me quite recently. It was from a paper from 2007, and he marked like the line, "Are reasonable operating system schedulers are fair?" And he's like, "Lol." And they were also talking in a paper about like if the scheduler isn't like fair, spin locks won't work, and I don't know. I think that's not true, but sure. Can you think of a scheduler that is reasonable and isn't fair? Anyone? Yes.
Any scheduler that has priorities?
Oh yeah, the answer was any scheduler that has priorities. Kind of yes, but fairness includes like the level of priorities because we're fair regarding the priorities. Any other ideas? Yes.
Maybe a real-time scheduler. So
yes,
when there are tasks which need to run at a specific time interval.
That isn't probably fair. Yes, but Linux already has a good one. Anyone else? Okay, one idea is just gaming, because we shouldn't be fair against everything else, because when you want a game, it should only prioritize and it should degrade all other systems. Only your game should run, because on the Steam Deck, you don't care about like the backup service working properly. You're like, it's a game. Anyway, but we can do more fun stuff. So one of the things that I did and presented at FOSDEM with Jay Killian from Facebook is I created an erratic scheduler. The idea is we can throw out like the fairness because but the other idea is most applications, they especially concurrent applications, they depend on the fairness. So they're like, the worker and the consumer thread and the producer thread, they are approximately getting on the CPU every like few milliseconds. But what if this isn't the case? Then it could crash. And that's still a reasonable scheduler because we can use it to find concurrency bugs. And that's pretty cool. If you're interested in more, there's a good LWN article written on our talk. And of course, in which languages is implemented. And now there's the small sponsor segment. No, essentially, I'm not a kernel developer at work. I work on Submachine. You probably all know SAP, and we are one of the biggest contributors to the OpenJK, so one of the biggest contributors to Java itself. And I'm working there on profiling. And I'm allowed to work a bit on the side, also on the scheduling stuff. And of course, you all know what's now coming, so hey, why can't we develop schedulers in Java? Yay! You're really excited about. Can we write them in Java? Yes, and we should. Anyway, it's pretty simple in Java. You probably all know the XKCD, where it's like, how do you fly? I just import anti-gravity, and that's how Python works. Here, it's pretty simple. We just implement the scheduler interface, and that's fine. We implement the methods as before, and it works, and we can implement our own schedulers. And that's pretty cool. For example, I implemented the erratic scheduler with it. It's written in Java, yes, and it works. Then we had a competition. I did a lecture at local university on this topic, and then a really cool student came later up and we launched a competition for people to submit weird scheduler, and he submitted a task clicker. You can run it on your system. It's pretty funny. It's written in Java, in Kotlin, and you can click on the task. So the task gets run, and you have to fight against the 30-second limit because your game will be killed. And what you see here below, I hope you can see it. You have kind of a syscall balance. So I think you can catch EBs, and thereby your system can do more syscalls. Your task can be more syscalls, and when it has exhausted its syscall balance, it isn't called it isn't scheduled. It's pretty cool what he did. So that's what you can do with you can have fun with schedulers. Consider this like 10 years ago, or even like 3 months ago, you couldn't do this because I think the student wouldn't come in and be like, okay, now I recompile my Linux kernel all the time, and when I have a bug in my game, yeah, I can trick my system. No, that's not the case. You can take a look at the scheduler, try it out. It's pretty fun. Of course, we can do something different. And you probably all saw that I brought something like this here. Let's see how it goes. And that's a scheduler that reacts to sound. You might have seen the video of Brandon Gregg where we were shouting at hard drives and showed that the latency changed. We can do this too. Let's see, we have the game before. We have the game before. Now, the cool thing is, I hope you see it all down there. Essentially, you see that it fluctuates a little bit. It essentially fluctuates by the loudness, and the louder it gets, the audio guys will like it. The more cores we have, so it's pretty simple. That's the calibration mode. I think I probably set the maximum loudness to something lower. Probably set it like to 10. I can tell you, shouting at your laptop is really fun. Go faster! And that's a scheduler. Okay, now it works. Good. I'm just removing the calibrate step. Okay. Okay, yeah, because of course there's is there a scheduler running? Yeah, there's a scheduler running. I should probably implement something that tells you, oh no, another scheduler is running. Anyway, cool. Now, but it's a bit pointless. Our system isn't on the line, blah blah blah. You all know the drill. It's a simple FIFO scheduler, by the way. It's nothing complicated. It's a simple FIFO scheduler. Let's call stress and G. That's pretty disappointing. You can be louder. Yes, all people think that my talk was so good you clapped out loud. Gaming the system. For the audio guys who are listening later to the video, I'm sorry. Oh, you see, when you laugh, it writes faster. Anyway, now, of course, that's a fun thing, but... So, you might have wondered why I'm having this here. Of course, you can extend it, because why just keep the loudness? Yes, I printed TPU SCHED logos as like softness. So let's see. The thing is, I modified the scheduler so that you can also do frequency scaling. So what frequency scaling typically means it is you give your scheduler target frequency, for example, 440 Hertz. That's like the Kammerton in Germany. We're in Chemnitz anyway. The invention of the Bandonium Tango at its heart, and Bach isn't far away in Leibniz. So yeah, that's and here let's do the calibration first. I need to frequency calibrate my audience, so I can show you. The slice varies. So we can check it. Should we try together? That's pretty good. Of course, this is just for show because they're too low. The only problem is when you want to get bigger ones, you only get them into esoteric shops where they're like, it's the sound of the moon and the earth, and I didn't want to pay $50 for something that's like sprinkled in stardust. So that's why there's, of course, a Spotify playlist. That's pretty good. Now I can show you that it really works. Sure. And I need to add stress and G, of course. Hopefully it does work. It gets irresponsive the more it gets irresponsive the closer. Yeah, it gets irresponsive the less close you are to the tone. I think we saw before that you're probably not as good as holding the tone, so it would probably, if I'm honest, we aren't fit to go into a choir. So let's go to the next scheduler, shall we? I hope you still enjoyed it. It's essentially we did frequency scaling. I think. Yeah, I like this much more. It's like the frequency scaling on your CPU. Anyway, what you could... Oh, of course. The only problem is with the scheduler that to work with it, I sometimes have to shout at my laptop to get back to the shell while I open stress NG. It's like, Arr! I can tell... I posted a video on Mastodon and I was out of voice afterwards. Anyway, let's go back. You can try the scheduler out yourself. You just go here, try it out. It's open source. It's pretty simple. Run vector. Oh, that's the wrong. Just go to my. It's not sound scaling. It's loudness scaler. Sorry for that. Just go into my GitHub user. You find it there too. And how it's implemented is pretty simple. So essentially, we have a FIFO scaler. We set the number of cores, we set the number of slices, the slice size, and we then just do a simple fast Fourier transformation on the sound. The cool thing is Java includes sound capabilities. That's the reason why I didn't implement it in C, because I didn't want to deal with all the sound things here. So another thing is, of course, we can also produce sound. The idea is we map cores to notes. I won't show you here because we've seen before the audio doesn't work. And if you have any policies ideas, just write them out. SCHED is really simple. We have it's still some work to do, and the verifier likes it when he thinks that you coded an endless loop, although you didn't. So it's still some work, but it's really fun. You can do is these are pretty cool schedulers. You can, for example, build your schedulers that enforce long time slices for specific processes to improve your benchmarking, because not being sailed away improves your benchmarking results apparently. So because it reduces variance, that's the thing that I want to do in the future. And you can do quite a lot of things. And if you have questions, just ping me later, or go into the Slack channel that's listed on the SCX webpage. Yeah, that's all here. I hope you liked the talk. If you want to learn more about SCHED, I post a blog post every 2 weeks at mostlynotice.de, mostly on things related to scheduling, related to eBPF, related to profiling, because that's what pays the bills. And you find the minimal scheduler, like the normal schedulers on there. Just go into my GitHub user where you find all the other schedulers. My team is at submachine.io. And that's all. Thank you.
Yes, thank you. Thank you. And the applause also goes not only to the scheduler. Any questions? We have some time.
No, why in Java is not a real question. I know it's interesting.
I have a question concerning the default scheduler in Linux, or maybe the possibility to have multiple schedulers for different kind of modes. If you want, maybe you want to do some heavy math computations. Is there some thoughts about?
So yeah, one of the ideas, and I think that's a really that's a feature that many people want, is to have C group specific schedulers that's in the works. The other thing is you can just look at the SCX repository. There are many schedulers that you can use for. We don't have yet code that's like type in, like with LLM type in. I want to have a scheduler that's done that. That sadly doesn't work. And Andrea really tried ChatGPT like coding of schedulers that worked interestingly, but yeah, it's still far away from the point where we have enough schedulers that we're like, oh, you want to do some math computation, use this scheduler, but we getting into this direction.
For the schedulers that have a user space component, is it highly recommended to special? For the schedulers that have a user space component, is it highly recommended to special case the user space component in the scheduler to give it more priority, or is that a stupid idea?
The problem is there are things that the problem is, for example, you have kernel tasks that your user land depends on, so it depends. You don't want to over-prioritize your kernel stuff because it's not doing real work in your user space, but I think most schedulers would probably don't differentiate that much, because you also have lots of different K workers on your CPUs. So I think most schedulers would handle them as normal, but I'm not an expert in scheduling. I'm just an expert in doing erratic schedulers and having fun.
So in the beginning, we were talking about the issues of multi-threading and all of this complex architecture. I mean, the examples that you showed us, I guess they were run on single threads, right? Or so my question is, are there any solutions to this yet? So
oh yes. So for example, people, for example, Rigi, who works at NVIDIA, he's working on that. Also, people, the folks at Meta are working on that to essentially create schedulers that know more information about your system, that take them more into account, and that, especially like with Layer, the thing that Facebook uses. The cool thing is you can configure it, so you can. Put proper affinities and more in this, and you can hardly configure it. But the cool thing is with SchedX, we're in the early days. So if you take a look in the SchedX, you will find that like only in the last half to 1 year, people really did anything with it. So you can still come into this and like me doing talks about this because it's so new. So I would really recommend you take a look in this because I think it will be more relevant in the future. And I think like when you come back in 1 to 2 years to a conference like this, you might be seeing schedulers that are focused on heterogeneous systems. But the problem is it's only out since December, and it's not readily available in most distributions yet. That comes with time. So I think we'll have to see in the future, but at least you now have the possibility to implement this. Even you have the possibility to implement something that, for example, improves performance in your specific use case. Of course, it takes time, but there are weekends. Anyway, any other question?
Thanks. Thanks for your talk. One question comparing to the other operating systems. So how does Linux with eBPF and now being able to write your own schedulers simply, does Apple and Windows offer the same functionality or?
No, as far as I know, they don't offer it. The problem is, of course, when you open up your scheduler, that's your core part, that's a pretty big thing to open up. And with Windows and Mac, you can't even change your desktop environment. So I don't think that they will open up that much, just because when you talk with vendors of operating systems, like with people from SUSE, they will tell you that it can be a pain when they expect the users to use their own schedulers and be like, my system didn't work. Yeah, you installed an improper scheduler. So I think I don't want to be the support guy answering these questions. I think there was one last question in front.
I wanted to ask about the term of fair scheduler. Does it mean scheduler fair towards threads, or could it also be a scheduler that is fair towards processes or users or other groups of threads?
It could mean everything. It's like in theory, I think it's probably fair to the tasks, but of course, if you implement a scheduler, you can be like, I want to be fair to the number of. You could easily implement something and want to be fair to the number of open calls so that every process is scheduled so that every process has the same number of open calls. That's fine, but I think in general it's probably meant to be fair towards the tasks. Is there any other question?
Okay, when not, I have one or two. Do you know how much resource you can allocate to that to eBPF, for example, to make a really complex decision logic? And the other thing, how does it interact with a C group? Or limit you can configure per process?
For the latter, I don't know. Probably you have to check it yourself. For the other thing, essentially you have the limit of what eBPF is allowed. For example, the verifier has to prove that you can only have like 1 million steps currently or so executed. So the decisions that you can make can't be too complex, but the cool thing is you can, what you typically would do in a more complex scheduler is you can put things out in userland. So you can have the really complex decisions like the planning problems where you, in the future scheduler, you could put AI on because that's what people like to do. You could could ask ChatGPT to give you something. No. But so yes, the scaling policies should be fast, because the main problem is when your scaling policies get really expensive, then it's like your system is only scaling. It should execute proper work, and even the FIFO scheduler isn't that bad. So in the end, you're like, you could be better off with just using the simple scheduler available. Yeah. But yeah, thank you for coming here. Thanks for singing with me to my laptop. I hope you liked it, and you can try to schedule out yourself if you want to shout at your computer to make it faster. And have a nice time in this lovely city.